Hi, good afternoon. How's everybody doing? My name is Yatharth Gupta. I'm a product manager at Microsoft. I run the Azure Databricks team. And we're here today with Paul Bruffett, who's the chief architect for data and AI at Devon Energy. And we're going to spend some time talking about how Devon Energy is using our product. So we're very thankful and grateful for Paul that he came and took this opportunity to come talk to all of you guys. How many people have heard of Databricks? The lights are getting in my eyes, but I look at a lot of hands going up. How many people are familiar with Spark or have used Databricks, not just heard about it? So what I thought I'd do is I'd kickstart by giving a very brief introduction on what Databricks is, how Microsoft thinks about it, and what we are seeing from customers. And then I'm going to invite Paul to talk about how Devon Energy is taking advantage of Databricks. So at a very high level, when we look at the big data analytics space across all of our customers and people who are not our customers, what we're seeing is that Spark is emerging as the leading analytics engine. So what we have done at Microsoft is we've looked at all the Spark distributions out there. We've looked at what our competitive offerings are. And we thought it would be valuable for our customers to provide them Spark that was designed and built to increase their productivity, built on a trusted cloud, and something that can scale to their needs. And not just scale up, but scale down as well. You could start very small and grow your workloads. It's Spark that's designed for cloud first. And how do we achieve that? If you look at most of the Spark distributions out there, you have to start with something like a cluster. You have to get into the technology first. We have designed Spark where a user who has very little knowledge about Spark could get started by eliminating all of the configuration options, making things very, very simple, and allowing our customers to focus on the business logic and driving value out of that. And that's been, the feedback on that has been very good. There's a quote from a couple of our partners who said that when they work on Spark, a typical POC would take them 2 months. This is from Blue Granite. And with Azure Databricks, that same POC that would take them 2 months is now taking them 2 weeks. So that's our goal. Our goal is to make sure that we make this super simple, super easy, so you don't have to focus on the boring parts. You get to focus on your business logic and drive up efficiencies. There are 3 big things that, and I apologize for the slide color there, but there are 3 big things that customers do with Azure Databricks. The first one is modern data warehouse. When customers have BI needs, where their end goal is to do something with BI, they're not only using a traditional data warehouse, but they're augmenting a traditional data warehouse with analytics that is done in Spark. And that's one place where we see Azure Databricks being used a lot. The second place is where the end goal is advanced analytics. Let's say you have a lot of data, you want to do machine learning, maybe you want to build a bot out of it, maybe you want to take that data and power a web app out of it. That's another place where we see people using Azure Databricks a lot. And the third one is real-time analytics, which is where you're doing predictive maintenance. Think about all of the IoT sensors that your company might have that are deployed out there, and you're getting all of this data back, and you want to very quickly predict what's going to fail. That's one example of machine learning in real time. There are plenty of others. Devon Energy is using Azure Databricks in all of these 3 scenarios. So we're super excited to see how our product gets used. And without further ado, I'm going to introduce Paul. And Paul's going to talk about how Devon Energy has been using this.
Thanks, Yatharth. Paul Bruffett with Devon Energy. So I am going to talk about all 3 of those scenarios. But first, a little bit about the company, because a lot of people don't really know who we are. So Devon Energy, we're a leading independent oil and natural gas exploration production company. We're headquartered in Oklahoma City, Oklahoma. We got over 3,000 employees, about a $22 billion market cap. And we produce about 541,000 barrels of oil equivalent per day. So that's gas, natural gas liquids, and oil. And we focus on unconventional hydrocarbons. So we can focus on horizontal drilling and hydraulic fracturing functionally. And so I'm setting a little bit of business context so you can kind of understand as I drill into the use cases here in a minute, really how that aligns to our business, right? And so the core of our business isn't really just drilling a hole in the ground and sticking a straw in it and getting oil back up, right? The wells that we drill are very technically demanding. They can be, in a lot of cases, over 2 miles long horizontally. So we drill down and then we drill over for 2 miles or about 12,000 feet, depending on the well, right? Some are longer, some are shorter. And the real challenge with that is that we have to stay within a pay zone, which can be 30, 70 feet. It kind of depends on the formation, right? But you think about you're thousands of feet underground and you're drilling over, right, for miles, and you're trying to stay within this pay zone. And if we don't, then we have a lot of negative repercussions, like our wells aren't performant and things like that. And so it's a technically demanding business from an actual technical execution perspective. At the same time, the oil and gas industry is under a lot of pressure to be cost efficient. So in the past, investors just said, hey, we want you to grow your reserves, we want you to grow your production. Now they say, I don't care about that stuff, I want you to be profitable. I mean, they care about that stuff to the extent it makes us profitable or not. So the question comes down to, how can we increase activity while maintaining technical excellence and controlling our costs? So I'm going to talk about how Databricks helps us solve some problems that really drive that business value. So we have a couple of topics that I'm going to enumerate, and we don't have 500 people in here, right? And so if you have a specific area that you want to drill into, don't hesitate to ask. We'll have time for questions also. And so kind of you guys help me with areas that you'd like to hear more detail on. But I'm going to start with the data hub. So we're using Databricks to reinvent our data warehouse and our integration landscape. And so we're taking our traditional environment that's been, our relational database systems, right? We've moved through several of those in increasing sophistication, but at the end of the day, we continue to run up against their limitations. Same for traditional ETL tools. We have the market leaders, but the challenge has always been our environment's not sufficiently agile, right? We have this web of integrations, with all the transforms built into proprietary systems, right? How can we kind of start to reinvent that and build it on open source platforms, specifically Spark on Databricks, and make our environment more agile and ready for the future? Then massive parallel processing for analytics. So we built an MPP system for subsurface analytics on Databricks. We'll talk about that. Distributed parameter tuning. So we have a lot of models that we build for real-time data. We do distributed parameter tuning, not just hyperparameters, but actually parameters for like feature engineering on Databricks to find sort of optimum combinations. And then finally, near and dear to my heart, is distributed deep learning. So we are doing distributed deep learning on Databricks using Horovod and the custom Databricks Horovod implementation allows you to use data frames directly into it. And so I'm happy to talk at great length on that to the extent it interests people. So I'm going to cover all of those kind of at a moderate level of detail, and then we'll see where we go from there. All right, so the data hub architecture. So I talked about that we're reinventing our data warehouse and our integration landscape. And so the data hub is what we're calling that reinvention, right? And so we're taking it, so our COO has said frequently that we're a technology company that drills for oil, right? And really what that means to me is that innovation, data, analysis, and technical excellence are really core to our business, right? That's fundamental to our success. And so data and technology are critical to who we are and our business bottom line. And so to be successful in innovation, we obviously need data, right? We have to say, well, this innovation is or is not being successful, and we evaluate that empirically with data, right? And so we are building a data lake and associated integration services, the data hub, to accelerate time to insight and improve our agility. And this is kind of our conceptual model, right, where the cloud data storage and processing, which I'm going to unpack in a subsequent slide, is then surrounded by APIs, either bulk read data services, which we've implemented in OData, using custom wrappers so people can connect to the OData services, do bulk reads, or these transactional read-write data services that we're continuing to evolve that allow people to actually plug in and kind of build their own extensible solutions on top of the platform. And then in the middle, we're doing our transform and our storage using a cloud data warehouse and Databricks. And so the idea is that in the past, we would build this web of integrations, right? This web of integrations between all of our different applications, some of which are on-premise, an increasing number of which are not, and then sort of serve all this proliferation of data warehouses that I assume all of you are probably all too familiar with. So we get a new use case, and we get a new team, or we get a new org, and they build their own data warehouse because the existing one doesn't meet their needs, right? So how do we start to bring all that together while at the same time improving our agility? And this is our answer for that, right? We're building this sort of ecosystem of services rather than saying, hey, let's bring a new thing on, let's wire it into all the other things, right? Which is what we've historically done. And so to unpack that a little bit, what we're doing is we're building this sort of data flow where everything flows into the lake, right? But the lake is a combination of services. And so to kind of walk through this architecture, we go from all our source systems, which are increasingly in the cloud, right? But I've enumerated a number of kind of traditional things like our data warehouse is SAP HANA. We've got a bunch of industry-specific applications like WellView, WellCore, Kingdom, Petra, all the different geophysical, geoscience apps that you use. SAP, all that kind of landscape. We replicate using a number of tools, including Attunity, which does near real-time replication. We use Azure Data Factory quite a bit. We're very happy with version 2. Great feedback from that. Great feedback on the Databricks integration for that. We're increasingly happy with the direction that's going. And we use Informatica, of course, because who doesn't, I think. We put that into Snowflake on Azure, so we're using Snowflake. We've been happy with that. We're one of the earlier Azure customers as far as I know. So Snowflake is kind of what I consider to be our structured data lake, honestly, because we just put everything there that's structured. And then Azure Blob Storage is the semi-structured, unstructured. So we have, like all oil and gas companies, we have a ton of binary data for like SegWi files and other seismic data, and we put that all in Azure Blob Storage with tons of images and logs and all kinds of things that go into Blob. And we use Databricks to combine those two. So the Databricks Snowflake connector is really effective. We've found that to be great. And we stage all the data into Snowflake. We do the transforms with Databricks. We write it back out to Snowflake, and then we consume it with either OData services, which is our preferred, or with the JDBC, ODBC drivers. And obviously with Databricks, we can merge it with that unstructured data, right? And so we take the structured data, we take all of our images that are associated to it, and we train our machine learning algorithms using Databricks. And then obviously we serve it up to tools, right? Excel, Power BI, Spotfire, SAS, all the things people know and love. So for this, the data hub is really the data replication, data lake, and that transform and access piece. And for us, this reinvents the data warehouse and integration landscape because now we've got all the data in one place, right? And for a lot of our users, it's been a kind of a transformative journey because the idea is always that we have everything in the data warehouse, but then as a geoscience kind of shop, we're saying, well, all of your data doesn't fit in the warehouse, right? Because it's tens of billions of records about subsurface points that we can't stick in HANA, right? It's just too much data to be cost effective. And so we said, well, all the data that we can put in the warehouse is in the warehouse, which means that they built other warehouses. Well, for us, we really do put it all in Snowflake, and we really do process it all with Databricks, right? Well, we still have HANA, but we're building this sort of agglomerated warehouse that really centralizes everything, including the data from HANA. And so now it allows anybody to build their own data and analytics solutions and share insights. So that's kind of been the other part of it. So as this data hub journey has gone on, we've really been focusing in the organization about citizen development or citizen empowerment, right? And so we're saying we've got all this data and we've got this great tool in Spark, and a lot of our users are very technical. They're engineers, they're analysts, they're people that know MATLAB or they know SAS or whatever tool, right? And so they're already very comfortable writing their own algorithms and doing some level of development. And more people are already coming to us and saying, hey, I built this great Python app on my desktop. I want you guys to do something with it, right? So our users are already out there ahead of us. What they're saying is, right now I get access to these 5 different databases to do my analysis, and I hook access up to it, and I need an easier way to do that. And we're saying, well, we've already got that, right? It's Databricks, where all the data is already in Snowflake. You connect Databricks up to it, and you write your Python or your Spark application. We actually support both. We use Databricks quite a bit for just running Python code that people have written. And for us, the advantage is that gets it off their desktop, right? Now all of a sudden it's not on their desktop, it's not on the network drive. They have the actual curated set of data to connect to, and they can publish their analyses for anybody, right? So everybody in the company has access to Databricks. And so we basically say, if somebody doesn't already have access, well, that was an oversight and we give it to them, right? And so we have tons of users in there, and people constantly build their own analyses and reports that in the past they would have had to talk to IT about. We have thousands of tables registered in Databricks, so all those tables that we put in Snowflake, we register in the data tab of Databricks. So people can just go in there and query them using SQL, right? And they don't care that Snowflake's underneath, they don't care about all that stuff on the left, they don't care where it came from. They already have the data, they're able to write Spark SQL, and then they're off to the races, right? Some of the powerful stuff that this has unlocked is people have these business questions that previously they were using Excel for, like one of our folks in an operating basin was saying, well, I don't know based on our current amount of drilling activity if we'll have enough water hauling capacity because our oil wells produce a lot of water. And so they were saying, what's the sort of probability that we will have enough water hauling capacity with the current rig schedule? Well, what if I change it by a week? Well, what if I change it by 2 weeks, right? And they did all the scenario planning themselves, writing custom code in Databricks that we weren't ever involved in. And they already had all the data, they already had all the tools, and they did an approved environment where they were able to share those analyses and insights with other business users, sort of end to end, right? They built the analysis, they shared it in Databricks notebooks or in Power BI, and didn't ever have to talk to us. So that's been hugely powerful for us and allowed people to be much more productive. So, yeah. All right, so let's talk a little bit about our subsurface analytics platform. So one of the key use cases for us is making people more productive. So drilling automation. So Devon monitors drilling and completions activities continuously. So in our Oklahoma City headquarters, we have a floor that is dedicated to what we call well con or well construction. And there are people, there are experts there that monitor drilling and completions activities around the clock. So what they're looking for is to say, well, I've got this well plan, which means this is the route the well is supposed to take. Is it on plan or is it deviating, right? And so they're getting real-time updates from drilling rigs and from completions crews with sensor metrics to basically say what's the pressure and what's the slurry rate and all these different things that come off of the pumps and things like that on completions crews. Or what are the sensor readings for gamma and things like that off the drilling rig. And so these folks are constantly looking at that data, matching it up, and sending guidance back to the crews in the field if there's something wrong. Well, this work can be very laborious, and it's hard to scale as our activity picks up. And so there was a time during the downturn that we had a single-digit number of drilling rigs active. And so this well-con crew didn't have enough to do. Now we have ramped that up significantly as prices have recovered, but we're trying not to increase headcount linearly, right? If we double the number of drilling rigs, we don't want to have to double the number of engineers that work around the clock to monitor those drilling rigs, because that's the place that we get into where it significantly impacts that profitability, right? And so we have to ask the question, how can we automate more work for experts like this, right? For these folks out in WellCon, who have to continually look at readings and manually match them up and say, I think the drilling rig is off plan, and so I need to call them and they need to go up or down, right? How can we automate that sort of matching, or how can we automate the identification that we have too much sand in the wellbore and we're going to occlude it, right? So to that end, we've used Databricks to build a subsurface analytics platform. So we're using Spark to process, analyze, and develop custom algorithms for geophysical data. And so these data sets can be massive. I mean, if we do a single seismic shoot, we end up with hundreds of gigabytes or terabytes of data that then we have to process or that our partners have to process. And previously, it was really difficult to scale this, obviously, on-premise, right? And so we've done a couple of things. One of the things that we're doing is we're moving all of our infrastructure to Azure, right? And so that's kind of the context within that my team works within. And so the data and analytics platform team kind of gets to ride that, right? That we won't have a data center that all the other teams have to build their own cloud native architectures, right? But at the same time, we're saying, well, now that we've got all the data there, because the rest of the teams are moving, right? So now we've got all our geophysical data, it's moving to the cloud. We have to unlock some new value by enabling people to analyze that data set in its entirety, right? And so we found, obviously, pretty quickly that we needed scale-out compute for that. And so we started with a couple of different platforms before we landed on Databricks. We've been using an on-premise Hadoop cluster for years, probably 5 or 6 years. We've used an on-premise Hadoop cluster. And we never really got the adoption that we wanted with that cluster just because it's really difficult to allocate the resources and to really allow our data scientists to get in and to build their own algorithms and to consume as much as they need, which we can easily do with Databricks. So we've said, hey, in this subsurface analytics platform, we have a number of clusters. Those clusters auto-scale. They automatically turn off, right? All the things you get for free with Databricks that we didn't get with other sort of even PaaS services, where we had to automatically allocate it. And if you've ever tried to dynamically scale some of the other PaaS services, you find you enter some weird edge conditions whenever you're going from really large clusters to really small ones that we didn't experience with Databricks. The other part of it too that's been much more productive moving this platform to Databricks is that in the past, whenever we scaled up, we had to say, well, this is how many Spark executors I'm going to get, right? And this is how many yarn containers I get to put those executors in. And if you don't line those up, you're not utilizing all of your cluster properly, right? And we have to make sure the containers have the right memory allocations and things like that. With Databricks, it manages all that for you. And so we don't really manage the amount of memory that our clusters get anymore or that our containers get anymore. We just allow them to dynamically scale and up and down and allow them to allocate themselves that way. So kind of with that in mind and the fact that that's made it much more cost effective for us to implement these algorithms, we've built algorithms to clean and impute missing data. So we have a system that takes all of the subsurface data we get and put it in one large database. And so that subsurface data looks like things like gamma logs or neutron density logs or porosity or resistivity. And if you're familiar with that kind of data, you realize that you end up with a lot of gaps, basically because these are sensors that go down in a well bore. And if they don't contact the sides of the earth, right? So if part of the well bore has fallen in, you have these large gaps. And so what we've used Databricks to do is to build algorithms to intelligently impute this missing data at scale. And so we're saying, well, we have tens of billions of records for this, and we have these gaps in this data, so we want to train algorithms basically to in a very pointed fashion, impute this missing data, right, algorithmically, not just something superficial like a median or a mode, right? And so we've used Databricks to develop these algorithms and deploy them on scale on data sets with tens of billions of records with all kinds of different log types from across the United States. And so that's been very effective for us. We've also used Spark to scale custom algorithms efficiently. And so this one is something where we have a lot of folks that are very good at writing Python code, they're very good at writing MATLAB code and SAS code. And so they can express the algorithm, sort of write their own algebraic functions to do things like curve matching, but they're not familiar with Spark, right? And so frankly, what we've done is we've taken those algorithms and we've made them fairly idempotent, right? Where one piece of the algorithm is independent of another piece of the algorithm. And honestly, we just wrap Spark around it. And so you have to still do some things to parallelize your data, right? Like distribute the data as variables that kind of fit in memory. But then we just basically find ways to break that algorithm up to operate on pieces of the problem space independently and parallelize it with Spark, and that's worked really well. And so functionally, we kind of just express the problem space, whatever that looks like if it's log matching or signature analysis, and we parallelize kind of a dumb algorithm with Spark that just really doesn't communicate forward or backward, and we collect all those results, and then we optimize the final answer. And so it's been very helpful to use Spark to scale custom algorithms without even completely recoding them. Like we still express the custom algorithms in terms of like SciPy and other algebraic libraries that are just generic Python code. And then we have our Spark experts come in and actually wrap that Python code that a data scientist has made in sort of a Spark wrapper that then parallelizes that, distributes it, and then we help them make sense of the resulting output, which can be non-trivial in some cases, but has made us a lot more productive, frankly, than saying, okay, well, I'm going to redo all of this from the ground up using basic Spark operations. The other really interesting kind of experiment that we've been doing is scenario planning and optimization. And so it's really similar to the thing I just spoke about where we're saying, hey, we've written some custom Python functions that take in certain parameters. So what we have to do is we're saying, hey, when we develop a field, how tightly should we space the wells? How many wells should we put on a pad? And if we put more wells on a pad, it's more cost effective, but they're also closer together. And in what order should we drill the wells? And so it's really this field planning, right, where it's an optimization problem. Where we're saying, well, we've got all these different parameters we could tweak about how we develop a field and what order we develop the field in and how tightly we space it. And how does all that really affect the timeline for developing the field and the total sort of recoverable product for the field? And so we're saying, well, there are custom algorithms that teams have written for this, but right now it takes days to run that, right? Because it tries to solve the things linearly, sequentially. And so we're working with that team to actually do exactly like I just talked about, where we're basically saying, hey, we're not going to rewrite all this code. We're just going to do almost like you do with like hyperparameter tuning and machine learning model. We're just going to run them all in parallel. We're going to take the existing code. We're going to wrap it in Spark. We're going to collect all your output from these parallel executions and kind of give you that resulting optimization space for the field, right? And so we're really starting to use Spark more as like a parallelization wrapper for existing code in some cases than a total ground up, I'm going to rewrite things and build in this framework. So I already talked a little bit about the last bullet, but the solution's gone through several iterations. Databricks involves the least developer friction of any of the solutions so far. And so I'll talk a little bit about it. So again, though, because we were previously on a PaaS service in the cloud, and our developers were honestly really unhappy with it. They were being successful, but there was a lot of friction that they were saying, hey, look, I'm constantly getting these cluster timeouts and things like that. I love that I don't have to patch it, but I hate that I have to do all this stuff to scale it. And I hate that I have to do all this stuff to optimize my jobs running on it. And we started kind of experimenting with Databricks and weren't totally sold on it. And then next thing I know, the developers are basically saying, oh yeah, I turned all of my PaaS clusters off and I'm doing all my stuff in Databricks. And so that kind of was the call for us to say, well, I guess we need to go all in on this, right? Because the developers spoke loud and clear in our case, and it has made them much more productive. And frankly, we've liked it very much. Another piece that I'll talk about with that subsurface MPP platform is reducing total cost of ownership and risk in the cloud. So whenever we built that subsurface analytics platform, we weren't really sure if our flagship use case of trying to predict the wellbore path, frankly, to predict, hey, where is the drill bit in the subsurface, we weren't sure if that'd be successful because not a lot of our peers in the independent E&P space are doing it. And so we said, all right, we'd like to do a prototype and we'd like to see if this thing works. Well, in the past, we would have had to say, well, we need to build a new Spark cluster, and that Spark cluster has to be really big because it turns out this problem takes a whole lot of processing for us to solve the way that we're doing it. And so we would have probably had to go and argue for about $1 million in hardware. It would have taken us about 6 months to say, well, who's the vendor we want to use? How large is the cluster? Let's get the servers. Let's rack and stack them in the data center. And so on premise to that second bullet, it probably would have taken us $1 million plus 6 months just to purchase and implement before we could say if we'd get any value out of it. So I don't know if the thing's going to work yet, but we need $1 million in 6 months to find out, which is a really hard sell in the current environment. And so we built this in the cloud. So we designed and built the solution in the cloud, which for us reduced the investment risk because now we don't have to spend that money up front, right? We're just provisioning cloud services as we use them, and it decreased our total cost of ownership. So the prototype was built in about 6 months. We basically said, hey, this thing's going to work. We like it and got good business feedback for about $150,000 in Azure cloud spend, roughly, right? Instead of that $1 million on-prem and 6 months added to the timeline. As a cloud solution, obviously if the prototype failed, we could have turned off the services and stopped spending on it, right? Because we're only committed to Azure. We're not really committed to a specific composition of services on that. And so we got the flexibility we needed and frankly had a much lower barrier to entry to even go out and try it, right? And now that it's been successful, we've actually been able to adopt it even faster, right? We don't have to build a detailed adoption plan / roadmap for our business and do proactive capacity planning. We just basically get to onboard them and turn the service on. And if we consume more of it, great. We see direct business value. And if we consume less, that's fine too. We can right size our spending as we need to. All right, so the next use case I'm going to talk about is more our model training and our distributed parameter tuning. So predicting events in the field. So we have a couple of use cases for this. So if the equipment fails, stopping production and necessitating expensive repairs is really challenging. What that really boils down to is we're trying to predict when equipment will fail, right? So we have all these things, all these moving parts, all these pumps and things like that out in the field. And we want to know in advance if that equipment's going to fail, and if so, when, and if so, is there something we can do to remediate that, right? To bring it back within operating parameters to prevent that failure. And so we built a couple models for that, and I'm going to talk about that. The other one is during completions job, specifically, we pump a ton of sand. We have hundreds of truckloads of sand in most of these new wells. And so as we're doing that, we can actually occlude or block the wellbore and that necessitates costly remediation. So we've also built models to try to predict that, to try to predict what we call a screen out, and prevent it, obviously. And so the real way that Databricks has added value to these two use cases is a couple-fold. So the very first one I'm going to talk about is both of these use cases are obviously using real-time data. So we get streaming telemetry data from the sensors or from the completions crews. And the real challenge for us has been, well, we have these fairly sophisticated pre-processing pipelines where we're saying, how should we do the feature engineering? How much time should we take into account? And what kind of other pre-processing should we do on the data regarding enrichment? And so the first is optimizing the feature engineering for the model, right? Well, exactly how should we pre-process the data to build the best model? And then the second is the pretty straightforward, how should we tune the hyperparameters for the model? And so for us, we really want to combine those, and we use Databricks to help us parallelize answering both of those questions, right? And so the first bit of it is we've had machine learning environments for a long time. How can we provide a standardized environment for our folks to build their models and be more productive? So we use the Databricks ML runtime. So if anybody has used that, it basically provides pre-installed libraries, TensorFlow, Horovod, XGBoost, distributed XGBoost, and that's all already installed for you, so you don't have to manage the versions or the interoperability. And so for us, that's been huge because we found that people would build their models and they'd use random libraries and random versions of those libraries that then they'd ask us to operationalize. And so the fact that now we're saying, no, you use Databricks, it's already all set up for you, it's already all installed in the ML runtime and maintained, which by the way, the other really big part of that is the CUDA libraries are already installed in versions that work with the installed version of TensorFlow. And so we can use it on GPUs with the libraries that are already set up and a version of TensorFlow that is already guaranteed to work with those libraries. And so the ML runtime has been really productive for us because now we don't have to manage that interoperability ourselves. So that's great. And I already talked about how frequently our users start with Python and they scale to Spark. So frequently they build their initial version of the algorithm, and either we help them with Spark as a wrapper to parallelize it, or we actually help them convert it to Spark if it's something like XGBoost where we need to help them with distributed XGBoost. The only challenge with that, obviously, is if you've used it, you know the Scala bindings are the only parallel bindings for that, which is the downside, but it's neither here nor there. So, like I talked about in kind of the preface to this, we use Spark to evaluate combinations of data pre-processing parameters and model hyperparameters. And so this is kind of a lot like the field optimization bit of it that I talked about, where I'm saying we have some of our feature engineering wherever possible in Spark. So obviously it's the most efficient for us to do our feature engineering and our pre-processing in Spark whenever possible, so that way the transforms run faster, right? That much is obvious. But whenever we have smaller data sets, we actually just do it with Python and then we wrap it in Spark to test all of the different combinations. And so we've coupled the hyperparameter tuning with things like the scikit crossfold validator, right, where it examines the parameter space and tries all the different combinations, and with the pre-processing pipeline where we say, well, what if we change how many days we look at for a particular pump, right? So if we say, well, let's look at the operating parameters for a pump for 7 days. Well, do we get more accuracy for 14 days? In some cases, we get less, right? Well, what if we combine two features in a certain way? Do we get more accuracy or not? And so in the past, that took a very long time, right? People have done feature engineering of that, pre-processing engineering and feature engineering of that kind for a long time, but it's been very time-intensive and laborious. And so we use Spark to parallelize that, where we basically express the problem space. It's kind of similar to the hyperdrive product that Microsoft started talking about this week. We express the problem space, right, and we allow Spark to explore that problem space in combination with the hyperparameter space, because sometimes there are knock-on effects that we really wouldn't have expected, where if we increase the time lag, the proper number of layers for our dense neural network changes, right? And so we explore both of those in tandem, in parallel, on Spark. And so that's been very helpful for us to sort of accelerate our model optimization. The other side of this, too, is then we promote the models to Azure Machine Learning Model Manager as endpoints for streaming use cases. And so what I've said is, well, we examine the best combination of features for the model, and then we explore the best combination of hyperparameters for the model. We combine those, we export the model, and we deploy it to the Azure Machine Learning Model Manager, so that way we can score it against streaming data, right? So in some cases, we do use Spark streaming with Kafka and express the models as that. But in most cases, it's much easier for us to deploy them as RESTful services, which this does. And then we can use a variety of solutions, and we're not really as tied to Spark or Kafka in that case. Honestly, it reduces our operational complexity for the model deployment, promotion, and life cycling quite a bit. And so that's been very helpful for us. All right, so probably my favorite use case, though, is using AI to process documents. So the business context for this is many of our well sites are remote, so they're out in New Mexico or in nowhere, or they're out in North Texas or wherever, right? So these are places that they're out in a field, like you see here, right? And this means that paper tickets are common, and PDF invoices and documents are emailed to us. And so a lot of these vendors, if you're looking for somebody to haul water in North Texas, you're not necessarily saying, well, the thing I care about the most is how great their APIs are, right? Our business honestly tends to not care that much about that. What they're saying is, I want somebody who can do it with a good safety record at a reasonable cost. Those are the things our business cares about for these types of vendors, right? And what that means for IT, though, is that these vendors will sometimes just leave a paper ticket in a box at the field site, where they'll say, I hauled this much water, and they put it in a box, and then they invoice us based on that, right? Well, and so we get all these different paper receipts, invoices, tickets, in some cases sensor readings. So in our Canadian plants, we have heavy oil plants up in Canada. They can't take things like iPads around there just for safety reasons and weather-related reasons. And so they write all their things on forms, right? And so we're saying we want to take all that, we want to extract the data from it in an automated way and do that at scale. And so just one slice of that is we received over 20 million invoices in 2017. And so we're saying, well, how can we automate that? How can we automate the extraction of the total and the date and the line items and the invoice number and things like that from these, right? Whenever in a lot of cases they're scanned invoices or receipts, right? And so the answer for that is distributed deep learning. And so we're saying, look, if we have just invoices, we have tens of millions of invoices for 1 year, and we have decades of invoices, how can we do deep learning at scale, right? On a heterogeneous set of data. And so what we do is we take that data, we do data processing and training for the deep learning algorithms using Spark, using Databricks. And so the first part of that challenge was actually we have them all as invoices, as PDF invoices that are scanned, and we have the extracted data in SAP. So somebody over the years has gone out and said, for this invoice, this was the total, and we have and so that's our training set, right? The labels are in SAP that they've extracted over the years, and we have a link back to the document or the image that it was actually keyed in off of. So that's great, right? We have, I don't know how many millions of training samples based on that just for invoices, but we have a lot. And so what we had to do first off, though, is actually OCR all that, right? Because it's not OCR, it's somebody actually just looked at it, filed it away, and keyed it in. And so what we did is we used Spark on Databricks to call the Azure Cognitive OCR APIs, so the Azure Vision APIs. And we actually lashed 12 of them together and wrote a custom Spark job to basically round robin between them so that we could get the scale we needed to, because I think the rate limit on those is about 10 a second, and that was honestly just too slow. And so we multiplied that by 12 and we got what we needed. And so we used Spark with the Azure Cognitive APIs. We processed all of our historical invoices, and I think it still took about 15 hours, but then we had them all, right? And so we say, okay, I've got the invoice, I've got the OCR, which comes back as a JSON payload, and I've got the labels. Great. So now we need to actually develop our deep learning models. And so we did that with TensorFlow and distributed with Horovod. And so the first challenge we said is, well, look, like, I can't even, well, even to take a step back, right, we had to do our feature engineering and our data pre-processing, and so we used Spark for that too, right? So we cracked open all that JSON, and we said, well, I want to start normalizing this out. I want to start bucketing it by vendor, right? And I want to start basically doing some clustering on it. Because we have similar types of vendors where some of them have very unstructured documents, and some of them have a high level of, or a high degree of structure within their documents. And so we said, well, let's do a little bit of clustering on these because we have thousands and thousands of vendors. And so let's figure out which ones we can probably have a high degree of confidence on and should focus on. And so we did a lot of data preprocessing and data mining using Spark on top of that output of the OCR. And then we took that in and we said, all right, now with this kind of understanding, right, with an understanding of the different types of data that we're going to work with, let's move that into TensorFlow and Horovod. And so, because this is all text, right, so it's got a structure to the documents. They're largely structured documents, but it's all text that comes back out of it. We used word embeddings, and we used different kinds of recurrent neural networks predominantly, right? And so we took all those word results and we vectorized them, and then we stored all that, and we end up with a couple 100 million training samples based on that. I say a couple hundred, but I mean just under 1 billion training samples based on that. And whenever I say that, I mean we've kind of decomposed some of the documents. A lot of the documents have multiple pages, and so our data set kind of exploded exponentially by the time we said that we're ready to start doing our deep learning, which meant that whenever we looked at it and we said, well, if we did this any way other than scale out on Spark, it would take, it would take us days just to finish, a couple of epochs with just a standard dense neural network, not even a recurrent neural network, which takes significantly longer for us to train, right, and to converge. And so our team historically had used PyTorch quite a bit more, but the Horovod estimator in Spark that Databricks has customized works with TensorFlow, frankly. And so the real incentive for us on that one was, if you use that estimator, you can actually take a data frame directly. And so you can preprocess all your data, you can load it in as a data frame, and then you can take columns from that data frame and provide them as the features for your machine learning model and for the targets for your machine learning model. And so now we don't have to really convert it to pandas or anything like that. We don't have to batch it off disk. We don't have to worry about running out of memory. We just parallelize it as a Spark data frame, and then each of those partitions is sent to different machine instantiations of the TensorFlow model, and all the gradients are averaged across those models. And so that's where Horovod comes in. And so if you're not familiar with Horovod, it's an open source distributed deep learning framework from Uber that works predominantly with TensorFlow and PyTorch. And so Horovod will allow you to parallelize without Spark. You can use Horovod, it exists predominantly independently of Spark, frankly. And you can use it to scale your deep learning models, but you still have to worry about either how do you batch it off disk or how do you fit it all in memory, right? And so for us, we were able to circumvent both of those problems and frankly to integrate our pre-processing pipelines, our feature engineering, and our deep learning pipelines in one notebook. And so what we found as we got down this road, which I'm sure everybody that's done a good bit of machine learning finds, is you train your model and then you say, okay, well that did or didn't work, so now I've got to change my features a little bit, right? I've got to do a little bit different feature engineering. And so to the extent we break those and put them in different products where we say, well, I'm going to use maybe something like Batch AI, which we like for deep learning, for my machine learning, and I'm going to use Spark for my feature engineering. We say, well, now I've got two different workflows that I connect, right? It makes our total cycle time longer, frankly, right? And so for our data scientists to have one tool where in a lot of cases they actually just had one notebook where they'd run their feature engineering and then do a training pass and run their feature engineering and do a training pass. It made the cycle time for iterating on their machine learning model much tighter, much faster, and shorter. And of course, I already talked about the ML runtime, but we were able to use clusters of we used the NC12 predominantly. So we used clusters of NC12 VMs, which have two of the NVIDIA K80s in them. And we found, true to Horovod's kind of inherent scaling, we found near linear scaling as we scaled our clusters. So there wasn't a lot of overhead there, which we were happy about. And so I already talked about this next bullet, one integrated pipeline for pre-processing and deep learning made iterating on the models much faster. So that was really good. The only challenge, if you've used the current Horovod estimator, the only challenge is really that you can't provide multiple arrays of features. So I can only provide one column of features, right? In a lot of our more sophisticated models, we have lots of arrays of features, right, that we want to pass in, and that's not currently supported. Databricks at their conference did announce a new initiative to improve that, right, and to generalize it. So the other thing that I noted kind of at the top of this bit of it is our team actually likes PyTorch a lot more than TensorFlow, at least in the last several months and year. and it currently doesn't support PyTorch, but their new Databricks new work does. And so we're really excited about that because functionally it decouples it a lot more than their current Horvath estimator does and makes it a much more generic solution. And so for us, kind of the value here in the integrated bit of it is we didn't really have to worry about like custom batching off disk or managing weird memory errors and things like that because we were able to do it all in one platform. The other side of that too is previously what we found whenever we were trying to allow our data scientists to do sort of scale out deep learning is really they just kept wanting to get their own data science VM that they never turned off. And so that kind of made it challenging from like a scale and a management and a costing perspective. And so using, we don't auto scale these clusters because if you do that, what you'll find is it actually gives you errors because different parts of your deep learning model suddenly died. And TensorFlow and Horvath don't like that, but we do auto terminate them. So we can't auto scale these clusters, we can't auto terminate them, and so it helps us a lot with our cost containment and management. And then the other side of that too is now we have an Active Directory integrated front end, whereas previously people were just kind of doing it off the side of their desk. And so at the end of the day, building that end-to-end pipeline here gave us a lot of kind of ancillary benefits and some sort of primary benefits around onboarding Horvath and things like that. So true to my word, I left a good bit of time for questions. So if anybody has any, I welcome questions on any of it, either the data hub and the warehouse bit of it, or kind of the distributed parameter tuning, or the distributed deep learning and Horvath and whatnot. Going once, going twice. All right. Oh yeah.
No? All right. That's fine. I can ask from here. So I noticed that you're using a lot of Snowflake there.
Yeah.
How are you finding the pricing against, let's say, ADLS or blobs or any other distributed databases?
Of Snowflake versus ADLS or blob?
For your purposes.
So for us, the analog would probably be less to those because we still use, so Snowflake specifically stores the data on blob in Azure actually, and we use Azure Snowflake. And so the pricing's actually the same because they just pass through the blob pricing. It's more for the compute side of it that we'd find, and that'd be more of a comparison for something like SAP HANA or SQL Data Warehouse. That'd be the things that we'd probably say would be more analogous. And we've found the pricing to be very competitive, frankly. And so, but kind of, so we found the pricing to be good, but really the Spark connector is what we were probably the most excited about. And so the Snowflake tables, we just register in Databricks and it passes the query straight through, including fairly complex join statements. And so whenever people are doing fairly complex Spark SQL joins that they don't know are in Snowflake, they're not using the Snowflake connector, we've just registered them. It passes the entire sort of syntax through and only returns the results. It does push down querying for it functionally. And so we've been very happy with it from that perspective. And it auto scales just like the Databricks clusters, the Snowflake clusters do. And so we've been happy with that.
What was your biggest challenge moving your data from on-prem up into the cloud?
For the distributed, like the big data environment?
Yeah, for the data hub.
For us, I think there have been a lot of challenges for other teams, and I'm sure our Microsoft team would be happy to talk about that in greater detail. But honestly, for ours, it's been great, frankly. So if I think about the challenges that we had with an on-premise big data environment, like our administrators spent all this time trying to patch it, trying to patch our Hadoop cluster. And at the end of the day, we added more and more things on there, like the SAS connector and the Informatica connector and Datamir and all these other products, which meant it took us like 6 months to upgrade the thing, which meant we were really far behind on the version. And so people were saying, look, I want Spark 2.0. And we were saying, well, we're still on 1.4, and I don't think we can upgrade it because we have to upgrade Informatica if we upgrade this. And if we upgrade that, we have to upgrade SAS. And so we never upgraded it. And the really nice thing about Databricks is we have a heterogeneous set of runtimes, right? Because honestly, I don't care what somebody else's runtime is on, right? And so we have one runtime for our distributed geosteering application. We have another runtime for our distributed Horvath solutions like I talked about, and then a whole ton of other runtimes. And so if you look at our cluster pane, we have like 30 clusters, right? And not all of them are on it at one time. That's also the point, right? but they all share the same backplane and the same control plane, and so we really don't have to worry about that. And then our Python libraries can be heterogeneous too, right? And so for us, it's kind of only been like upshot. We get way more adoption of the current platform than we got of our last platform, just because we tell everybody you can come in here, because the other side that I'll talk about, and then I'll consider the question answered, I think, is the other side that I didn't talk about is what we were deathly afraid of on-premise is that we'd have some data scientists that go nuts on the thing and he'd impact a production workload and make us miss an SLA. That's frankly not a problem now, because we just give that guy his own cluster and we say, do whatever you want, you only get 6 nodes though, right? And then all of our other environments are automatically running, they're off, and they're happy, and they're really not impacted by that, right? And so for us, it's been kind of nothing but upside on our team, frankly, as far as I'm concerned.
Thank you for sharing the insight. Great digital transformation example. Just a similar question, little similar. How did you guys move your on-prem SDFS data from Hadoop to cloud?
How do we move what data to the cloud?
The Hadoop data.
Well, so for us, we kind of, like historically, we were doing a bunch of truncate and reloads of data sets into Hadoop. We just did it every night because you got a 10 gig backplane and a flat network hierarchy, and honestly, you might as well use it because it's all in one data center, or we had 2, but still. Now that we're in Azure, though, it doesn't make a lot of sense to do that, right? And so we reimagined our integration. We reimagined kind of the hydration of the data lake, if you want to say that, which is why we brought Attunity, frankly, is because it made it much easier to replicate the data. And so what we did is we basically said, look, we need the same kind of outcome as we have on-premise, which is to have the data there, but we're not really going to take any of the way we used to do that forward. We're going to kind of throw that all away and we're going to reimagine it. And to that end, we've said, hey, we're using Azure Data Factory for some workloads, and we use it for both ETL kind of stuff or ELT kind of stuff, and we use Attunity for other workloads. And then we've written custom jobs to replicate the unstructured data that I talked about. And so we didn't really say, well, I'm going to take what I've got and I'm going to shift it over. We said, I'm going to take what I've got and I'm going to throw it away, but I'm going to take a year to do that and I'm going to refactor everything, frankly. And for us, that's kind of how we've unlocked the value of the cloud, in my opinion, is we've said, hey, we're going to go all paths. We're not going to do it the way we used to do it. We're just going to do the same things differently. Does that answer your question? Okay. Any other? Oh, yeah.
I got a question about the operationalization of the machine learning and the data science that you described.
Yeah.
I'm kind of curious where you still see the biggest friction in the whole kind of process from creating a model, training the model, then deploying it so that you can score with it, and then retraining it after some time.
Yeah, I mean, I think you actually just described it, at least at the high level. So the thing that we still have a challenge with, and actually Microsoft has made a couple of announcements around it that I look forward to testing. But honestly, it's taken that entire life cycle. It's that model. It's kind of the development life cycle for the model that you just articulated, and it's putting it in one place. And so it feels like we have a really mature set of tools around the software development life cycle, but it feels like that tool set doesn't necessarily translate to the models, and it feels like it's not there for the models. And so Databricks did announce ML Flow. I don't know if you've seen that. And so that feels like it's one attempt at the problem. It's definitely not there because they just announced it and it's 1.0, and maybe it's 0.8, I don't know, but that feels like other people are acknowledging the problem you articulated and trying to solve it. For us, we really try to just put as much as we can into things like scripts and into things like Azure Data Factory and put it into VSTS where we can, right? And so we check our models in as kind of binary objects or into something, and we check in the model pipelines into something like VSTS, and we try to put the release process in there. But I think we're really going to be looking for things like the pipelines that Microsoft has been talking about, and the DevOps for AI that I think they've been talking about, and try to hope that some of that solves it. Because frankly, right now it's scripts, honestly. But Azure Machine Learning Model Manager does make it a little easier because they can they wrap some of that for you, but it only solves like that last mile problem, in my opinion, today. Any other questions? Sorry, could you, there's a mic right there, could you?
What was the final percentage of efficiency on those million documents that you were able to convert?
So that's a good question. It largely depends on the thing we were trying to extract, right? So we were very, very accurate for invoice number, right? Because invoice numbers were very unique kinds of objects that we found on there. I'd say overall it was in the high 90s, but there are some features where it's the low 90s if they're a little more esoteric and a little bit harder to disambiguate. Like we have many kinds of dates, many different kinds of dates that appear on the same invoice, and they can be very difficult to disambiguate one from the other, right? Well, this is a service date, and this is an invoice date, and this is a delivery date, right? Like that can be very difficult to distinguish. And so for those, it's usually a lower, right? But for things like the total, it's high 90s, right? And so we were able to continue. And I think we have a lot of room to run on that, frankly. I think we can drive that down a lot further, but we're still working on it.
Thank you. You know, why I asked that question, I come from a very similar industry challenge. You know, we are trying to solve a zillion documents in our rural setup.
Almost everybody, yeah.
Very interesting. Thank you.
Yeah.
Are you able to share the magnitude of your Snowflake environment as far as the size of your storage environment and potentially the amount of nodes you guys typically have functioning?
So honestly, we're still onboarding a lot of our use cases. So right now it'd be hard for me to articulate that, I think, except in cost terms, which I don't think I can do. So, so frankly, it's kind of a hard question to bring back. What we've found is, though, that whenever we connected it to Databricks, we got really good performance from like a Snowflake medium or a Snowflake large. And honestly, we got a lot of work out of those, and we had to really work to scale past 4 mediums or 4 larges. I mean, like, because whenever we were evaluating, we actually wrote a Spark job to evaluate it, to basically do concurrency testing with JDBC connections. We wrote a Spark job to open a bunch of JDBC connections, several thousand at a time, frankly. And we were able to, with unique queries, because Snowflake does caching, right? And so we were able to get several thousand through concurrently with for reasonably complex queries with 4 or 6 mediums at a time, you know, and we have a lot of those. We probably have 6 Snowflake clusters for different use cases, but we'll have several terabytes of structured data. I mean, tens or a couple hundred terabytes maybe, whenever we're done. But yeah, I mean, so far it's been great. We like it with Databricks so far. Any other questions? Well, if anybody else has a question, I'll be up here for a minute, so feel free to ask. Thanks.
Thank you, Paul.